So this is basically the data that you will be looking at to select the particular pump. Now, this is a very simplified diagram. Why? Usually a pump curve contains a lot of lines. So this is your pump performance line. Similarly, you will have an RPM line, you will have an efficiency line, and you will also have an NPSH line. Now, why are there so many complex things? Why is this pump performance curve so complex? Well, that's because the system is so complex. And if you are just using total head and flow as the only requirements, then you will definitely be able to get a pump. The problem is it is not going to be efficient. Now, you really don't care about this efficiency a lot if you're basically if you're just building, if you just have one centrifugal pump and you're using it for residential uses, right? It doesn't matter. But in an industry, you need a lot. Guys, I would appreciate it if you can not play with the annotation tool. All right. So in an industrial application, what's going to happen is you will need a lot of pumps. For example, if you take automotive companies, even for just a single shop floor, they would need a lot of centrifugal pumps to transfer fluid. All right. So understanding this curve is very, very important. So let's talk about this curve. So on the x-axis, you have flow rate. So this is basically high flow rate, and this is basically total head. So if you basically want to transfer fluid to a very large height, then the flow rate is obviously going to be lower for a particular pump, right? But the truth is there has to be a minimum flow rate. There has to be a minimum flow rate at which the pump needs to operate. Can anyone think of a reason? Why should we have a minimum flow rate at which the pump needs to operate? The main reason is if you have very less water, then the amount of heating is just unbelievable. You would still transfer some amount of fluid, but in the process of transferring fluid, you will heat up the entire system, and that can actually damage your electric motor. So there needs to be a minimum amount of flow rate. And there are several factors. Even in your houses, if the sump water level is really low, right, these type of problems can happen. The electrician would come and say that the motor has burnt, right? So there needs to be a minimum flow rate at which the pump always needs to operate. And then let us say that you're slowly increasing your flow rate requirement. So I'm going along x-axis. As I'm continuously increasing my flow rate, then what's going to happen is my pressure head, the pressure head, or the height to which I'm able to transfer the fluid, that is going to decrease. And as you're going through that path, you have a lot of issues. For example, you have something called as low flow cavitation. So let me ask a simple question. What does cavitation mean? It's not backflow. So backflow is basically occurring when there is a pressure difference, when there's a negative pressure difference. Charul Gupta, one kind of a loss, yes, but what is that loss? Apur, the bubbles hit the blades, that is correct. But how are those bubbles formed? Vaporization of water due to low pressure. Exactly. Samir Gupta is exactly correct. So what's happening is at the eye of the impeller, the pressure is very, very low. And when the pressure is lower, what we have learned from TS diagrams and PV diagrams or material diagrams is your boiling point is reduced. All right. So if the pressure keeps on dropping, there's a particular pressure called as vapor pressure. And this changes as a function of pressure and temperature. So what happens is when your pressure is keeping on dropping, your molecules, your water molecules are automatically going to start, the interface becomes highly unstable and boiling starts to occur. And you have vapor formation. All of the sudden vapor is formed inside your liquid. And this is called as cavitation. This is pretty bad because these bubbles will go and impact your impeller. And over long term, what can happen is it's first going to damage your impeller. And if the cavitation is severe, right, because if your impeller geometry is incorrect, then you can have a lot of cavitation, right? And that can cause for more cavitation. And in the process, the impeller can get so much damaged that it will actually contact the volute or the casing of the centrifugal pump, and that is going to lead to system failure. All right. Now, in addition to this, pumps that are used for industrial uses, they always don't carry water. They sometimes carry a lot of chemicals. They sometimes basically they sometimes carry non-Newtonian fluids, right? Why why bubbles create cavitation? Alok, maybe try rephrasing your question, right? So depending upon these industrial applications and depending upon the fluids that you are using, the problems can vary, right? So these are the things that you would consider while you're picking up a pump. And usually there is a point called as best efficiency point. It is called as the ideal zone. Why? When you're selecting a pump, there will always be variation. There will always be variation in the flow rate. You cannot get exactly the flow rate that you want. There will always be some variation. And this variation needs to be in a zone where you don't have a lot of cavitation issues, where you don't have NPSH issues. Okay, what is NPSH? We'll talk about that. That's a new term that I'm talking about. So we'll come back to this. So you'll start seeing NPSH issues as well. So as an engineer, when I'm designing pumps, I need to make sure that I improve my volute design, I improve my impeller design, so that these type of issues are less frequently occurring, right? So that is the design, that is the objective of a pump designer. Now remember, a pump designer is not a person who actually just modifies the CAD model, right? So that is basically a CAD engineer. A pump designer is someone who basically has a thorough knowledge of fluid mechanics and basically says that, okay, I'm going to change the curvature of my impeller in such a way that at this particular flow rate, I have less cavitation. All right. So that concept, right? That concept is usually substantiated with some kind of theoretical model. And then it is then given to the CAD engineer who will basically create the model. And then the CFD engineer takes it from there, runs the model, and basically verifies if that is happening or not. So overall, the system is actually quite complex. And in order for you to understand what's happening, like for example, how the cavitation is getting created and what is the location of cavitation, right? In order to understand this, CFD is kind of the only tool. Why? You can actually use low speed cameras. That's not a problem at all. But when you use low speed cameras, when cavitation occurs, you don't see anything because the bubbles are going to completely block your vision. So if you use CFD, then there are a lot of visualization techniques that you can put in use to understand where this cavitation area occurs.